Hello everyone, in our previous studies, we learned that functions are mathematical models that describe patterns of change. Monotonicity is an important property of functions, and derivatives can quantitatively characterize the local changes of a function. So is there a connection between these two, and what is the connection? Today we will explore this issue. Firstly, please consider this question. Figure 1 shows the function ht of the center of gravity of a diver relative to the water surface height h as a function of time t, which is negative 4.9 t squared plus 4.8 t plus 11. Figure 2 shows the function vt of the diver's velocity v as a function of time t. This is the derivative of ht. The image is equal to negative 9.8 t plus 4.8. Among them, a is equal to 24 of 49. B is the 0 point of the function ht. Actually, we know through calculations. X equals a, which should be the axis of symmetry of the ht function graph. At this point, t takes all real numbers. Of course, it can also be seen that a is also the 0 point of the function vt. Please think about it, everyone. What is the difference in the movement state of athletes from takeoff to the highest point and from the highest point to entering the water? How to describe this difference from a mathematical perspective? Actually, by observing the image, we can know. From jumping to the highest point, athletes are in the rising stage. Therefore, the height h of its center of gravity above the water surface increases with time t. So at this stage, ht monotonically increases. T belongs to the open range, and ht monotonically increases from 0 to a. Correspondingly, since a is the 0 point of the function vt, so at this stage, the derivative of vt, which is ht, is greater than 0. Similarly, from the highest point to entering the water, athletes are in a declining state. Therefore, the height h of its center of gravity above the water surface decreases with the increase of time volume. So at this stage, ht monotonically decreases. When t belongs to the open interval a to b, ht monotonically decreases. Correspondingly, at this stage, the derivative of vt, which is ht, is less than 0. That is to say, the speed is opposite to that of the rising stage. So it is not difficult to see from this question that there seems to be some connection between the monotonicity of a function and the positive value of its derivative. So please think about it. Can we use the sign of the derivative to determine the monotonicity of a function? Based on the previous question, we can boldly make such a conjecture. On a certain interval a to b, if the derivative is greater than 0, then the function monotonically increases over that interval. On an open interval a to b, if the derivative is less than 0, then the function monotonically decreases on that interval. Before we verify this hypothesis, let's first use some familiar functions to verify. Please observe the graphs of some functions below. Can you explain the relationship between the sign of the derivative and the monotonicity of the function? Let's take a look one by one. Firstly, for the proportional function fx, it is equal to x. By taking the derivative, we can obtain its derivative function as 1. And discovered, in the open interval from negative infinity to plus infinity, the derivative is always greater than 0. Observing the graph of the original function at the same time, it can be seen that the function monotonically increases in this interval. So it can be seen that the proportional function fx is equal to x, which satisfies our conjecture. Next, let's take a look at the quadratic function fx, which is equal to the square of x. By taking the derivative function is 2x. And it was found that in the open interval from negative infinity to 0, the derivative is less than 0. On this interval, the original function monotonically decreases. Meanwhile, in the open interval from 0 to positive infinity, the derivative is greater than 0. On this interval, the original function monotonically increases. So the quadratic function fx is equal to the square of x, which also satisfies our conjecture. Next, let's take a look at the cubic function fx, which is equal to the third power of x. By taking the derivative, it can be concluded that the derivative function is 3x squared. And it is known, on the open interval from infinity to 0, the derivative is greater than 0. On this interval, the original function monotonically increases. At the same time, in the interval from 0 to infinity, the derivative is also greater than 0. And within that interval, the original function is also monotonically increasing. So the cubic function fx is equal to the third power of x, which also satisfies our conjecture. Finally, let's take a look at the inverse proportional function f(x), which is equal to 1 of x. By seeking differentiation, the derivative function is negative x squared. We can roughly draw its image. And observed, in the open range from negative infinity to 0, the derivative is less than 0. On this interval, the function monotonically decreases. Meanwhile, in the open interval from 0 to infinity, the derivative is also less than 0. And on this interval, the function also monotonically decreases. So the inverse proportionality function f(x) is equal to 1 of x, which also satisfies our conjecture. It can be seen that so many functions conform to our hypothesis. From this, we can almost obtain some relationships between the monotonicity of a function and the sign of its derivative. We speculate that there is a relationship between the monotonicity of a function and the sign of its derivative function as follows. On an open interval a to b, if the derivative is greater than 0, then the function monotonically increases on that interval. On an open interval a to b, if the derivative is less than 0, then the function monotonically decreases on that interval. But in fact, we cannot draw conclusions based solely on these few exceptions, because mathematics requires rigorous reasoning and argumentation. So please think about it. Why is there such a relationship between the monotonicity of a function and the positive number of its derivative? We can actually explain it from the geometric meaning of derivatives. The functions we study are all continuous. For example, such a function. So, we know that at x0, the geometric meaning of the derivative is that the function y is equal to the slope of the tangent of the graph of f(x) at point x0, fx0. So, if the derivative is greater than 0 at x equals x0, then the slope of the tangent at that point is greater than 0. So the tangent at this point should rise from bottom left to top right. And when we learn the geometric meaning of derivatives, we know that there is a very small area near x0. The tangent can be used to approximate the function f(x) curve itself. So, it also means that the graph of function f(x) is rising. The function monotonically increases around x equals x0. Furthermore, if the function has a derivative greater than 0 at every point on a certain interval, so the function near each point on this interval is monotonically increasing. Therefore, the function monotonically increases throughout the entire interval. Similarly, from the geometric meaning of the derivative, we know that if the derivative is less than 0 at x equal to x1, the tangent at this point should decrease from top left to bottom right. Therefore, the graph of function f(x) also decreases. That is, monotonically decreasing around x equals to x1. Furthermore, if the derivative is less than 0 at every point on a certain interval, so the function decreases monotonically near every point on this interval. Therefore, the function monotonically decreases throughout the entire interval, so we can intuitively verify the conclusion of our conjecture. However, if we want to explain the truth more deeply, we need to return to the definition of monotonicity of functions, the concept of derivatives, and their geometric meanings. Please think about this question. Can you explain the geometric meaning of the function y being equal to the average rate of change of f(x) and the relationship between the positive and negative derivatives? Firstly, we take any 2 points p1, x1, fx1 and p2, x2, fx2 within a certain interval. So the average rate of change represents the ratio of fx1 minus fx2 to x1 minus x2. Through previous learning, we know that this equation represents the slope of the tangent line connecting points p1 and p2. If the slope of the tangent line connecting any two points on a certain interval is greater than 0, this means that for any x1 or x2 in this interval, when x1 is less than x2, fx1 is less than fx2. We can see from the definition of monotonicity of functions, the function f(x) monotonically increases in the interval, and from the image, we can intuitively observe. On this interval, for each tangent line, there is always a tangent line parallel to it. So if the derivative is greater than 0 on this interval, this means that the slope of the tangent line connecting any two points is greater than 0. Thus, we can demonstrate that the function f(x) monotonically increases over this interval. Similarly, for a derivative less than 0 on a certain interval, this indicates the situation where the function monotonically decreases on this interval. Prove that they are similar. Everyone can use their own analogy to verify after class. So, we have truly obtained the following relationship between the monotonicity of a function and the sign of its derivative function. On an open interval a to b, if the derivative is greater than 0, then the function monotonically increases on that interval. If the derivative is less than 0, then the function monotonically decreases over that interval. So, please think about it. If the function fx is in the open interval a to b, there is always a derivative equal to 0. So what are the characteristics of functions? In fact, if a function is in an open interval a to b, there is always a derivative equal to 0. This means that the slope of the tangent of the function at any point on the interval is 0. So at every point on this interval, the tangent is horizontal. Therefore, at this point, the function fx is a constant function. So through the research above, I hope everyone has a profound understanding of this conclusion. Next, we will use the relationship between the monotonicity of a function and the sign of its derivative to solve some example problems. Please take a look at example 1. Use derivatives to determine the monotonicity of the following functions. Let's first clarify our approach. I want to use derivatives to determine the monotonicity of a function. Firstly, we need to clarify the domain of the original function, then obtain its corresponding derivative function through differentiation operation, and the sign of the derivative function can be determined by solving inequalities, based on the relationship between the monotonicity of the function we just explored and its derivatives, to determine the monotonicity of the original function. For example, the first question. Because fx is equal to the cube of x plus 3x, we can first clarify that the domain of the function is R. So by taking the derivative function can be obtained as 3x squared plus 3. Organizing can result in 3 times the square of x plus 1. And since the domain is defined as R, therefore, it can be known that within the domain, the derivative is always greater than 0. Therefore, based on the conclusion we just studied, we can know the function fx monotonically increases on R. We can use the properties of a function to roughly draw its schematic diagram, as shown in the figure. The second question is because fx is equal to sine x minus x. Among them, x belongs to the open range from 0 to pi. By taking the derivative function can be obtained as cosine x minus 1. And since x belongs to the open range from 0 to pi, so it can be seen that within this range, cosine x is always less than 1. Therefore, the derivative function is always less than 0. At this point, it can be inferred from the conclusion we just explored. The function fx belongs to an open interval in x and monotonically decreases from 0 to pi. The image is shown in the figure. The third question. Because fx is equal to x divided by x minus 1, we can organize the formula, get 1 minus 1 of x, and it can be known that x belongs to the open interval from negative infinity to 0, and the open interval from 0 to plus infinity. Next, the function can be differentiated. Obtain its derivative function as 1 of x squared, and it is known that within the domain of definition, the derivative is always greater than 0. So we can know from the conclusion, the function fx monotonically increases in the open range from negative infinity to 0 and from 0 to plus infinity. The image is shown in the figure. Therefore, we can use derivatives to determine the monotonicity of a function. Next, let's take a look at example 2. The information about the derivative function is known as follows. Let's try to draw the approximate shape of the fx function graph. Let's first clarify our approach. In this question, we know the sign of the derivative function on different intervals. It can be based on the relationship between the monotonicity of the function and its derivative. Determine the monotonicity of the original function on different intervals one by one, and roughly depict the graph of the function through monotonicity. Therefore, the process is as follows. Firstly, when x is greater than 1 and less than 4, the derivative is greater than 0. So it can be inferred that the function monotonically increases over the open interval 1 to 4. When x is less than 1 or greater than 4, the derivative is less than 0. So it can be known that the function monotonically decreases in the open range from negative infinity to 1 and from open range 4 to additive infinity. When x is equal to 1 or x is equal to 4, the derivative is equal to 0. So these 2 points are quite special. We call them critical points. So in summary, we can roughly draw the graph of function fx, as shown in the figure. So the above is the content we explored in this lesson. Now let's summarize the class. In this lesson, we focused on exploring the monotonicity of functions and the relationship between the positive and negative derivatives of these functions. That is, on a certain open interval a to b. If the derivative is greater than 0, then the function monotonically increases over that interval. And if the derivative is less than 0, so the function monotonically decreases over this interval. That's all for today's class. Goodbye, everyone.